Hello, good day everyone. Today we are going to learn radioactive decay in 15 minutes with me, Hanis, Amira, Binti, Ahmad, Nazri. And this is for the subject of PQI 6019. I hope you will enjoy throughout the class. Let's go. For today's topic, we will be covering Chapter 6, Nuclear Physics. Our learning objective is students should be able to explain with examples decay equations of alpha decay, beta decay, and gamma decay, which is the Learning Standard 6.1.1. Well, students, what is actually a radioactive decay? A radioactive decay is actually a process where unstable nucleus becomes more stable by emitting radioactive radiation. But now the question is, what is a radioactive radiation? These are the types of radioactive radiation. Number one is alpha particle. This is best represented by helium-4. Number 2 is beta particle. Beta particle is best represented by electron. And the last one is gamma ray. Gamma ray is best represented by the symbol of gamma itself. So, these are the three types of radioactive radiation that you should know. We will now start with the first one, which is equation for alpha decay. Alpha decay. Alpha particle is a helium nucleus consists of two protons and two neutrons, making the nuclear number is 4, and which is why it is called helium-4. The unstable nucleus releases alpha particle to become more stable nucleus of new element. As you can see, this is the alpha decay equation. X will decay into Y plus He4, where X is the parent nucleus, Y is the daughter nucleus, and alpha particle is the radiation that have been emitted in this decay, which is why it is called an alpha decay. Now, let us continue with number 2, which is the equation for beta decay. Beta decay. Beta particle is a fast-moving electron, where unstable nucleus decomposes into one proton and one electron. But only proton will stay in the nucleus while electron is emitted with high kinetic energy. This is the beta decay equation. As you can see, X will decay into Y plus electron. X is the parent nucleus, Y is the daughter nucleus, and E is beta particle that is emitted for this decay. Number 3. Equation for gamma decay. Gamma decay. Gamma rays are high-frequency electromagnetic wave. Unstable nucleus releases its excess energy. Gamma rays have no mass and neutral, which literally means gamma ray have no charge. This is the gamma decay equation. Unlike alpha decay equation and beta decay equations, X will decay into X plus gamma. As you can see, the final product is not a new element, but it's the same element, which is X. What happened actually is, initially the nucleus is in excited state, and after the decay, the nucleus X is with lesser energy, since the excess energy have been emitted as gamma ray. It is now time for exercises. Let's test your understanding on this topic on alpha decay, beta decay, and gamma decay. Let's start it. For question 1, write an equation for the radioactive decay of the element and state the type of radioactive decay occurred. Number 1 Roman is the decay of thorium-232 into radium-228. And number 2 Roman is the decay of radium-228 into actinium-228, which is the isotope of radium. Let us see number 1 Roman first, which is the decay of thorium-232 into radium-228. The solution is, by using radioactive decay equations, we will see this equation. Thorium-232 will decay into radium-228 plus X. Since we didn't know what is the radioactive radiation emitted, we will be using the simultaneous equation to search for the nucleon number and the proton number. Okay, let us go for the nucleon number first. 232 from the left side of the equation will be equal to 228 plus A from the right equation. So, by solving this, A is equal to 232 minus 228, and the nucleon number will be 4. As for the proton number, 90 from the left side of the equation will be equal to 88 plus Z from the right side of the equation. Z is then equal to 90 minus 88, and the proton number Z will be equal to 2. Since we have obtained the nucleon number and the proton number, now let us substitute this number into the decay equation. So thorium-232 will decay into radium-228 plus helium-4. Now, as you can see, helium-4 is an alpha particle, which means this decay of thorium-232 into radium-228 will emit an alpha particle. Therefore, the type of radioactive decay that occurred in this decay is alpha decay. Now, let us proceed with number 2 Roman, which is the decay of radium-228 into actinium-228, which is the isotope of radium. As for the solution of this decay, we will use the radioactive decay equation. Radium-228 will decay into actinium-228 and emit X. So, now how are we going to search for the nucleon number and the proton number of X? Did you know? Yes, yes, very good. We will use the exact same method as number 1 Roman, which is we will use a simultaneous equation to search for the number of nucleons and the number of protons for x. As usual, 228 at the left side is equal to 228 plus a at the right side. After solving the simultaneous equation, we will get 228 minus 228, exactly like what I have written here at x. And next, for the proton number, 88 from the left side is equal to 89 plus z at the right side. Therefore, if we minus 88 minus 89, we will get negative 1. So, let us substitute the answer for the nucleon number and proton number into the equation. And you can see the decay equation is now like this. Radium 228 is now decay into actinium 228 plus electron with nucleon number 0 and proton number negative 1. Aha! Did you see this? This is actually a beta particle. It is an electron. Therefore, we can conclude that the type of radioactive decay is beta decay, since the decay process from the decay equation showing that it emits beta particle. Now, let's continue with question 2. Determine the number of nucleons A and number of protons Z of element lead when polonium-210 undergoes alpha decay. So, the first thing that you have to do is to extract the information from the question. As you can see, the parent nucleus is polonium-210 and the daughter nucleus is lead Pb, and it will emit an alpha particle since it undergoes alpha decay. As for the solution, we will be using the equation for alpha decay. X will decay into Y plus helium-4. As we just stated just now, we have extracted the information, isn't it? Now it's time to substitute the information into the equation. Polonium-210 will decay into lead plus helium-4, but we are still looking for the nucleon number and the proton number for lead. So, do you still remember how are we going to settle this? Did it? Yes, very good. We will still be using the simultaneous equation, where 210 minus 4 and 84 minus 2 for lead, and we can finally receive the number of nucleon for lead and the number of proton for lead. So polonium-210 will decay into lead-206 plus helium-4. Therefore, the number of nucleons A is equal to 206 and the number of protons Z is equal to 82. I guess that is all for today. Thank you so much for your attention, and thank you so much for lending your ears to hear my video. Have a good day, everyone!